Now, I've just gotten through telling you that there's a whole range of densities at which if we make random formulas, we get formulas which are satisfiable but hard, which we believe take exponential time. Well, of course, we don't actually know that any of these take exponential time, because we don't know that p and np are different. If p and np are the same, well then sat is in p, no matter how big or how random or how dense our formulas are. So, nevertheless, you might be tempted to think that, oh, can we change this sort of physics picture of these random problems and their hardness into a proof that p and np are different? Can we actually prove that these random formulas are exponentially hard? If you can prove that any case of an NP problem is exponentially hard, you've proved that p and np are different. So a number of people have tried to do this, but I'm sorry to say it doesn't really fly. Let me explain why, by introducing yet one more constraint satisfaction problem. This one will be XOR sat. What is XOR? It means exclusive OR. You know, in natural language, when people say OR, they often mean exclusive OR. So the logical OR, classically, is this is true, or this is true, or maybe both are true. And our sat clauses are perfectly happy if 2 or 3 of their variables are true, as long as at least one is. But in natural language, if I say, I think I'll have the chicken or the fish, presumably I don't want both the chicken and the fish. That would be way too much food. So exclusive OR means this is true, or this is true, but not both. And if I have 3 things, well, it actually means that an odd number of these are true. If you like modular arithmetic, this is like addition mod 2. If each one of these is 0 or 1, it says that this plus this mod 2 is 1, which means an odd number of these 3 things are true. All right, well, this is yet another kind of clause. We've already seen sat clauses, not all equal sat clauses. What the heck? Let's think about XOR sat clauses. Well, here's a little formula. I've written it as a little system of equations. But in fact, we can think of this as a set of linear equations, because the XOR really is just the sum of these 3 things. It just happens to be the sum mod 2. Now, if you've taken a linear algebra course, you already know that if I give you a system of linear equations, then using techniques like Gaussian elimination, you can tell whether it has a solution, and you can find a solution. And whether you've done this before or not, all those same techniques work perfectly well for mod 2 arithmetic, just as they would work for normal integers or real numbers. So XOR sat formulas can be solved in polynomial time. XOR sat is in P. Because unlike an OR, as in sat, which is really a nonlinear operation, XOR is a linear operation, and we can solve systems of linear equations. But the interesting thing is that the physics of random XOR sat problems, all this stuff about the bumpy landscape, the clustering, the freezing, all of that actually looks very similar to random 3-sat. So what's going on? If this landscape is all bumpy and the clusters are all frozen, why is it that we can solve XOR sat in polynomial time? Or why isn't it, if indeed it isn't the case, that we can do this for sat? Well, when you think about what you do when you solve a system of linear equations, you're not just making little local moves like, oh, let's try flipping this one variable from a 1 to a 0. You're really doing a global rewriting of the system or redefinition of the system. Let me remind you what we do. We do things like subtract one entire row from another entire row. We're essentially saying, instead of thinking about the original variables x1 and x2, I want to think about a new combination of these variables, like x1 minus x2. I'm redefining the terms of the problem. And with that kind of global redefinition, using the tools of linear algebra, we can eventually simplify the problem until the solution is staring us in the face. Well, on the other hand, if I tried to solve XOR SAT with a local search algorithm that flipped one variable at a time, or if I tried to solve it with a simple genetic algorithm which made little mutations, or if I tried to solve it with a standard backtracking algorithm which tries to set one variable at a time and backtracks if it hits a contradiction, all those algorithms fail miserably and take exponential time for XOR SAT, just as they do for SAT. Because those types of algorithms are stuck wandering in a bumpy landscape and getting stuck, missing frozen clusters and all that stuff. Remember before, when we looked at a couple problems like multiplication, and we found that the simplest algorithm, the one that we naively thought was the best, isn't the best. There was a subtler, more global kind of divide and conquer algorithm which was much faster. Well, that's what's going on with XOR SAT. There is this global algorithm from linear algebra which solves it. Meanwhile, the kind of naive local search algorithms all fail. But gee, how do we know that there isn't an analogous global algorithm for SAT? How do we know that there isn't some move we can make analogous to reshuffling or adding and subtracting the rows of a matrix that will simplify a SAT problem and make it simpler and simpler until we can solve it in polynomial time? Well, we don't. We don't know that there is no such miraculous algorithm, which is kind of why we don't know that P and NP are different. So, this is what the physics tells us about the random problems. This is what it reveals to us about how the shape of the landscape affects many types of search algorithms that we're used to, but it doesn't eliminate the possibility that there's some utterly different kind of algorithm which sidesteps the landscape completely and manages to jump or soar over these frozen clusters and directly find a solution. But remember, if such an algorithm works for SAT, it works for every problem in NP, thousands of problems in that family tree, and everything, including mathematical proofs, that is easy to check is easy to find. So I don't believe it. But it's certainly fun to think about.